Welcome every science and physics enthusiast to this third lecture on the series of general relativity. In this video, we will unravel a fascinating connection between Newton's laws of motion and the fundamental concept of geodesics in general relativity. How do these seemingly distinct theories align and converge under specific conditions? Newton's laws of motion, which have stood as the cornerstone of classical mechanics for centuries, describe the behavior of objects under influence of forces. General relativity, which is Einstein's revolutionary theory that defined our understanding of gravity, at its heart lies the concept of geodesics, curved paths that particles and light follow in the fabric of space-time under the influence of gravitational fields. Our goal today is to journey through this transformation to witness how the complex mathematical framework for general relativity seamlessly reduces to the elegant simplicity of Newtonian physics when the conditions are just right. This striking connection not only bridges these two monumental theories but also highlights the classical foundation embedded within the depths of Einstein's revolutionary work. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to episode 3, where we are trying to understand how from Newton's laws of motions, the geodesics of particles and how they are related to each other. Before we go ahead, those who have missed my first and second episode, you can very well look into the I button, but I would like to give you a very quick recap on what we have covered. So in the first and second episodes, I have covered mostly about special theory of relativity, that the laws of physics are identical in all frames of reference with no acceleration. I have also talked about that the speed of light in vacuum is the same for all observer. Both time and spatial distances are no longer absolute. We also came to know that there is some amount of inadequacy in Newtonian mechanics which deals with inconsistent with the behavior of objects moving close to the speed of light. We have also seen that Einstein was influenced by the idea that there is no absolute frame of reference, and he posited that all motions are actually relative. We also looked into that when in 1905 he proposed the special theory of relativity. It introduced the concept that the laws of physics are the same for all observers in uniform motion and the speed of light is constant for all observers. We also looked into the second episode, what was the real motivation behind special theory of relativity. First was the invariance of the speed of light. That experiment result contradicted classical physics, which assumed that the light would vary. We also saw that it was not clear how this consistency with the speed of light could be reconciled with classical mechanics. That means inconsistent with the electromagnetism. And we also found that the Michelson Morley experiment showed that ether does not exist. All of this taken together actually speaks of a transformation in our thought, a transformation in terms of equations. And what we saw over in the last few episodes is that the laws of physics in this frame of reference and this frame of recurrence, when they actually transform, there's a way to relate the observation. So when this particular truck, when it is overseed over an aeroplane, we see that observer in these vehicles need to describe their own motion. So the velocity of one particular car, how it gets transformed into other. So in all, what we can say, it helps to understand relative motions. So this is a particularly important, these scenarios, these transformation equations were required for celestial bodies, particles and accelerators, etc., so that we can really understand why the transformations are required. Most importantly, what we notice that these transformations are required so that the laws of the physics should remain same. For example, GPS satellite requires them to transform equations based on their own coordinates. We also found that the transformation equation enable us to compare observations, and there is a unique versatility, that is with the same physical system, different using different coordinates or frames of reference. We found that these are required also because transformation reveals the insight of a physical phenomena. We can know more. Transformation equations have been tested and confirmed countless times, and the transformation equation is used in special and general relativity. and which is necessary for the effects of relativistic motions in gravity. So in all, what we can say that transformation equations are the fundamental tools, and it ensures that the consistency and predictability are maintained under the observation of the physical world. One of those transformations actually talks about the Galilean transformation, where we saw that the laws of physics are, when transformed from one frame of reference to the other, they are actually resulting into the same result. So result would be x and x, and we found that the laws of physics are the same in all inertial frames of reference. So it allows us to describe how events appear, and the significance of Galilean transformation is that they provide a way to compare the results of experiments which are actually performed in different inertial frames. We also saw this example that the ball which is going up and during a person observing within the train would appear just like a parabola. So from the perspective of an observer standing on the ground, the ball travels in a parabolic arc, and this actually shows that because the observer on the ground is moving relative to the train. We also saw in the last few episodes what is the Michelson Morley experiment, that with the sound waves and electromagnetic waves, James Clerk Maxwell tried to define his theory of electromagnetism taking into account with ether. Then Edward Williams Morley and Albert Michelson actually used this Michelson Morley experiment, which finally proved there is nothing which is called the existence of ether. If you want to know about Michelson Morley experiment, you can go back to my second video where I have explained in details. We also found that the principle of relativity, that c, the speed of light, was the same in all directions, which actually helped Einstein to form the, I would say, the basic tenet that the law of physics are the same for all observers. And the postulate that the speed of light is constant in all frames of reference actually came from Michelson-Morley experiment. We also saw something which is called a Lorentz transformation, where this gamma factor would show what is a Lorentz factor, and you can look into the mathematics into my earlier videos, which I am not explaining here. We also saw this one, which is called a Lorentz factor, which takes in account into time dilation, length contraction, etc. And the Lorentz transformation is relativistic, and that is why it is considered as a fundamental and crucial concept in Einstein's theory of special relativity. Also, we noted that Galilean transformation is valid for low speeds, but it won't transfer as per the Lorentz law because it is much smaller compared to the speed of light. We also found out the implications which are called the length contraction. This is a kind of a schematic diagram which shows how length of an object contracts when it moves close to the speed of light, and we have seen this type of I would say implications. The equation has been much more explained in details in my last video. We also saw what is called a time dilation, and here if a twin, both of them travels, the time travels so slower, so when he comes back to the earth, this person had aged more and this person have aged less. Apart from that, we also accounted in what is called the geometry of space-time, where we saw that general theory of relativity, all this parallel transport, covariant derivative, Christoffels symbols, geodesics, these are more of an understanding of curvature, and that is why it is more intuitive in nature and contains a lot of exotic mathematics. From here we moved into the transition of relativity to geometry, all this transferred into tensors, geodesics, parallel transport, etc. We also established in the first video that general theory of relativity is a classical theory. That means if you're standing at point number 2, suddenly you don't know where you are at point number 1 or where will you go. So the system is irreversible. That means state 1 has no past. And an irreversible system cannot be defined by the laws of classical physics. Only what we can do is that we can find out a probability in case of a quantum world, which led Einstein to form his famous quotation, God does not play dice. We also saw that there is a lack of inherent probability in terms of general relativity, and that means there is a conservation of information, and we can in principle predict a system's future evolution with certainty. That means there is no loss of information or probabilistic guesswork. From there we came to a very important conclusion that general theory of relativity is a field theory, and a deterministic equation is guided by Einstein's field equation. So if we know a system and given its initial conditions, speed, time, velocity, whatever, we can predict the future behavior. So when I talked a lot about the last recap, because this is important. Now we will start with our discussion for this video from here. Now, considering that if there are certain initial conditions which are given and we can predict a future behavior of a system, definitely it is called a classical system. Question comes that if general theory of relativity is a classical theory, does it obey the classical laws? Also, it provokes us to think that if there is a classical law, then is there any relevance with the classical Newton's law with the laws of general relativity? And can we derive equations of motion from the classical laws, or we can go back from the general relativity laws into the classical physics? These are the questions which we are going to answer, and we are going to see that if we call general relativity as a classical system, does it obey the laws of classical physics? Let us find how general theory of relativity obeys the laws of classical physics. Coming in the next part of the video, we will go back to none other than the celebrated Sir Isaac Newton. We will look into one of the fundamental laws of Newton's laws of motion. So we will see that we will start with a function that describes the position of an object of a time. So let us denote that as x of t, representing the position of the object time t. And we take the first derivative of the position. So what we do is that we take the first derivative of the position with respect to time to the object, considering velocity as v, and we get simple. Velocity is a change of position with the change of time, which you have written as dx by dt. Now, once we have done with the first derivative position, we look on to the second derivative position. So to find the acceleration a, we take the derivative of velocity with respect to time, which yields into this. As you can see highlighted, this is velocity, which is again differentiated with respect to dx by dt. And what we get from here is that we know that v is dx by dt. So first we have taken the first derivative of position. We have started with the position function. Now I have taken the second derivative of position. Now what we do is that we all know, I'm not repeating this, that we know what is called the chain rule of calculus, that is derivative of an outer function times the derivative of the inner function. And if I apply the derivative to this dx by dt, which represents velocity, we get this. Now those who are watching, you can take a note, d square x by dt square. What does it tell? This tells something very important. This process shows that the second derivative of the position function with respect to times gives us the acceleration of the object. This is very important. And in summary, what we can say that by differentiating the position function with respect to time twice, we can arrive what is called at this kind of an equation. Now I want you to take a note of this acceleration, what we got as the second derivative of the position function. Now this is what Newton's laws of motion using simple calculus tells us. Now the question is that can this Newton's law of motion is in some way related to finding out the geodesic, which is the same thing as movement of particle but in a curved space-time in general theory of relativity. Let us find it out, but first I would like to tell you what is a geodesic, coming up in the next part of the video. First, we will understand the basic idea and concept of a geodesic. So you see in geometry, geodesic is a curve which represents, I can say, some sense of the shortest path on a Riemannian manifold. Let us ignore what is a Riemannian manifold. We are not interested into that. But what we are interested is that it represents the shortest path. Now, if I say that it is a generalization of the notion of a straight line, it won't be wrong, because straight line is something which we take place in terms of Cartesian coordinates, straight, I would say Euclidean space. But once we generalize things from straight line into further curvatures, it becomes what is called a geodesic. So it is basically derived from this Greek word. Geodesy is coming from a Greek word geodesia, which means division of earth. So as you can understand right from the root, it is something which is related to the measurement, division of the earth, and so on. So geodesy is basically a science of measuring and representing the geometry, gravity, and spatial orientation. Two most important things. It is the science of measuring the size and shape of the earth, and a geodesic is the shortest route between 2 points on the earth's surface. Now remember, here is a misnomer. Shortest routes are, geodesics are not always the shortest curves between 2 points. It is only shortest when we take something only locally. right? So though the two concepts, like the shortest curves and geodesics, are related to each other, but technically they are not the same, because the difference is that geodesics only locally take shortest distance between points, and they take it something at a constant speed. Now when I talk of only locally, it actually gives rise to what is called a differentiable manifold. Obviously I'm not going to explain differentiable manifold in this video, but you can look into my other videos of differential geometry, where I mention what is a manifold, what is the definition of a manifold, and how a differential manifold actually manifests or shows something which is local. So geodesics are the shortest path, straight line or something which are connecting two points, and it is measured, or it is a kind of a generalization of a straight line, but technically it should not be confused with shortest curves between 2 points, because it is only shortest when we are considering a manifold or a differential manifold. Let us see this part into a visual idea. So you see, this is the Earth, and this green line, the great circle, is considered to be a geodesic on a sphere. This straight line connecting between A and B, they are also something which is very familiar to Euclidean geometry, and it can be considered as a shortest path between two paths. So we can say that a geodesic is the shortest path between 2 points on a curved surface. So in geometry, it often describes as a curve that locally minimizes the distance. So on the shortest, on a sphere, the geodesic is maybe the great circle. We can have triangles, etc., which I have not explained. So this is just to let you know that given a manifold, given a kind of a surface, it actually shows the shortest path, or the shortest path between 2 points. Let me show a very quick example. So does the equation change in curved space-time? Yes, it does. Because here you see, these are basically these different points which I am connecting. This is a curved surface, and these are the two lines. Again, they are connecting. This is what it is connecting. This is connecting between 2 points. Okay, so if I take a tram, which path it will move? It will move in this way. So the question is that all these things in a flat space or a curved space, they actually denotes the closest point or the shortest path between 2 points. Question is that does it actually change the equation in a curved space-time? Let us look in the next part of the video. So this is the geodesics are simply the shortest path between 2 points. Okay, so in general theory of relativity, geodesic, as I told you, it generalizes the notion of a straight line. Now why we have generalized? Because we are not into Cartesian coordinates, we are into some crazy curvilinear coordinates where the straight line needs to be generalized into further details. So we can say, in other words, a freely moving or falling particle always moves along the geodesic. We are considering freely because we want to make things very easy, that there are no external influences. Taken a straight line, here is a ball, it would move in this path. That means the ball will roll in a straight line because there is no force. Taken this kind of a curved surface with this ball, it will obviously move here. So the ball will roll down the hill because the curvature of space-time is there. And here you see in the next line, the ball will not roll in a straight line. Instead, it will roll in a curved path because it is considered to be the geodesic path. For the ball, it is a straight line. So here comes something very important. Note that the curvature of space-time is what causes the particle to accelerate. We will see in the further lectures in this series that this causes gravity. So in the absence of any external force, there are no external forces which are taking place here. The only force acting on a particle is the gravitational force, and there is not a gravitational force even, it is the curvature of space-time. So the ball is rolling down the hill not because of gravity, it is because of the curvature of space-time. This is flowing in a nice straight line because the curvature is straight. So whatever be the curvature, the path or the free falling particle flows along with that, and that is called a geodesics. So as you see here, I was talking that does the laws of the equations change? Yes, it changes, because we cannot carry with this kind of a Pythagorean formula when we talk of the curve space. And what we need is a tensor which calculates the length of curves, infinite simular distance, and various other things. However, we are not covering tensors. This is just to give you a basic idea that equations do change, and the Cartesian or the Pythagorean rule does not apply here. Now we come to the central part of our video. What is the geodesic equation? What is the geodesic equation? Let us look into the next part of the video. It looks, although a little bit cumbersome, but we will take a step-by-step approach to explain this. First of all, you see this ds square, this is actually the proper time. Now, it might happen when you're reading literature, blogs, or watching videos, ds can be shown as a d tau. So don't worry about this tau or s. It actually means that we are computing the proper time. So what does this equation overall in simplified language explains? It explains that it describes the paths of that freely falling particles for test particles follow in a curved space-time. These paths are equivalent to straight lines in curved space. So you can say that what was Newton's laws of equations were predicting us in a straight line, the same thing is being done with this geodesic equation. Let us take these parts which will be easier for us to understand. First of all, we will just take this one. So this is what this terms actually represents the second derivative of the coordinate x mu. Now, why we are taking x mu? It will come slowly clear. So it is a second derivative of the coordinate x mu with respect to proper time, which is the tau or s, whatever, which is the time which is measured by a clock moving along the particle. So what it does, it describes the acceleration of the particle along the geodesic. Here you can go back to Newton's law, that also expresses as a second derivative acceleration. We will see a comparison, don't worry. Now what is this all about? Gamma, mu, alpha, beta. These are called Christoffels symbols of the second kind. Now hold on, I will just explain you what is Christoffels symbol and why it is called of the second kind. Now, Elwin Bruno Christoffel, a remarkable German mathematician who contributed a lot in terms of differential geometry. Actually, Christoffel symbols are used to define the covariant derivative, which is again a generalization of the ordinary derivative in order to take into account the curvature of spacetime. If you want, you can go to my video on what is a Ricci curvature tensor and Riemann tensor. I have explained what is called a covariant derivative. So you can say the ordinary derivative really doesn't work in terms of curvature of spacetime. Again, just like straight line is extended to geodesics, covariant derivative is an extension of the ordinary derivative. So Christoffel symbols actually are of two kinds. The first one is called the first kind, which is defined in terms of the metric tensor G, which we will come later, and the second time is defined in terms of the covariant derivative, and that is why it is called a second order differential, because the Christoffel symbol is second because they are defined in terms of the covariant derivative, which is a second order differential operator. So there are two kinds. We are dealing with the second because it is a second order derivative, and we have seen that first order in terms of metric tensor can also be done, but however we are not dealing with that. Okay, so we come to this Christoffel symbol. Now you see what happens over here. They are related to the curvature of space-time, involve the derivatives of the metric tensor. They encapsulate the effects of gravity on the geodesics, and the Christoffel symbols, if they measure the curvature, if it is 0, that means it is in a flat space-time. Okay, so this part, this mu, actually denotes the index or the coordinate in which the covariant derivative is taken. And this alpha beta, this actually shows what are the coordinates. So if I see this alpha beta is equal to beta and alpha, then we say that the Christoffel symbols are symmetric, but only in case of the lower indices. Now when I say symmetric, it actually means that it actually follows the mathematical property which is known as the symmetry property. Now this symmetry property is very important. And what we can understand is that more a curvature of a space or a manifold is, the larger will be the Christoffel symbols intuitively. And in flat space-time, it is absolutely 0 because it has got no curvature. Now this property, this symmetric property, has got a profound influence in many important aspects of general relativity, in terms of metric tensor, in terms of the way they are calculated, in terms of the particles which are following. However, I will explain it later. But try to understand that the geodesic, the Christoffel symbol are symbols which are symmetric in the lower indices, and this follows the symmetry property, which means there are further implications which are further important. So we go back to this part. We have done the first, the second and the third. So what we here see is that this term represents a coordinate, say for example x alpha with respect to proper time, the first derivative, indicating that the velocity of the particle is along the geodesic. Similarly, x beta is the first order derivative with respect to proper time s, which involves the indicating the velocity of the particle along the geodesic. And the geodesic equation, when it is written out in the coordinate of mu, is a set of second order partial differentials. So what we summarize from this? We summarize that the geodesic equation general relativity describes how particles moved in curved space-time. The Christoffels symbols capture the curvature of spacetime, and the equation ensures that the particles follow a path of least action in this curved time. So from here, let us look into these three equations. The first is the geodesics, the second is the Newton's law of motion, and the second F equals to ma. I hope you all know. Now the reason I have written this three equation is to show you a kind of a comparison. Now you see this x alpha is the first derivative of the coordinate with respect to time. Here also you see dx is the first derivative of the position function with respect to time. We see ds squared and dt squared or d tau squared. These are again in respect to proper time. Although the concept of proper time is more relevant in relativity, in classical physics we call it time. Here you see d square x mu. This is the second, this term is the second derivative of the coordinate x mu with respect to proper time s, and d square x also, this process shows that the second derivative of the position with respect to time gives us the acceleration of the object. Now see how beautifully we derived or we understood the relation between geodesics equation, which is typical to general theory of relativity, although geodesic is taught mostly in differential geometry, and how the second and the first derivative and the time derivative, all of them beautifully matches with Newton's laws of motion. From there we take this kind of an understanding that under weak field approximation, that is gravity is low, there's a little amount of dust, etc., the geodesic equation gets reduced to Newton's law of classical mechanics and vice versa, and we have established that general relativity, being a classical system, obeys the law of classical mechanics. Here is a nice comparison. The feature, Newton's second law and geodesic equation, you can just go through. This is to Newtonian gravity, this is to general relativity. It is applied in non-relativistic. It is both non-relativistic and relativistic in terms of weak field approximation. Accuracy, good approximation in weak field, more accurate in terms of high speeds. There is only one question which is keeping you busy. I can understand that why we have reduced the geodesic equation equal to 0. Why it is not 1, 2, 3 or something else. In order to answer this equation, we need to look into this, what is called, maybe you already know, the principle of least action. So what does the principle of least action tells? It tells that the equation of geodesics is set to 0 because it describes the path of a particle that is moving freely without any external forces on it. In other words, we can say that a particle is moving in a straight line in a curved space-time. So here it moves along this path. That means for this particle it is a straight line in a curved space-time. It moves without any external interferences. Here is the Lagrangian, which is the classical Lagrangian, but remember that the condition is set to 0 is equivalent to saying that the particle's acceleration is 0. This means that the particle is not being pushed or pulled or any direction, and it's simply coasting or moving nicely along the curvature of space-time, which shows that it is taking a curvature and it is moving in a straight line, which manifests into something we call it as gravity. So the particle is not being pushed, it is just staying over there, and the curvature is dictating in which way it will move. So it is set to 0 for the simple reason to make it that we get the Lagrangian of the entire history without any external influences, and it takes the least possible path. Now hold on, this is the Lagrangian in classical mechanics, but in general theory of relativity we get a curly L. This curly L is known as what is called the Lagrangian density. Question is that why we are taking Lagrangian in classical mechanics and why not Lagrangian why Lagrangian density in general theory of relativity? That I will be speaking in the next part of my video. Why we need a Lagrangian density and why change from Lagrangian to Lagrangian density, we will cover in the next part of the video. So here is a quick summary from today's lecture. What we understood is that we proved general relativity as a system which is classical. We showed how Newton's law and geodesics are related. What is a geodesic? What is its component? What is the Christoffel symbol? What is the first and second kind? Why is that the geodesic equation is set to 0? And what is that we move from Lagrangian to Lagrangian density? So finally, what we can say is that general relativity, being a classical system, obeys the rules of classical mechanics, and how beautifully it, under weak field approximation, Newton's law either way gets merged into general theory of relativity, just as all the small rivers, they strive and go and merge into the vast ocean. So thank you very much for those who have really watched this video. I would immensely thank you for taking up your time. If you have liked the video, please click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID, and you can subscribe to my other channel of General Theory of Relativity. You can further follow me on my Facebook, Instagram, LinkedIn and Twitter channel. I think this is going to be a good understanding in terms of understanding Newton's law of motion, geodesics. Physics for Students will continue with this general theory of relativity and other videos, but till then, goodbye.